this problem's a little bit interesting. I am asking not for an antiderivative. I am asking for the antiderivative of this function. But I'm asking for the antiderivative that has this property that the big F of 0 is equal to 2. Now, the idea here is this. If we think about the general antiderivative of this little f, it's going to be some function big F plus an arbitrary constant. So there's a whole infinite family of different antiderivatives depending on what the value of the constant is. But by plugging in this number, for one of the values of c, you're going to have it that when you plug in 0, it's going to be equal to 2. In other words, this claim about the f of 0 is equal to 2 is basically going to tell us what that c value has to be. So let's try to figure out what the general antiderivative is first, and then we'll try to evaluate the c. So I need to come along here and figure out what my f of x is going to be, my capital F of x, my antiderivative of a little lowercase f of x. Now, I know the derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x just the same. So this is, first part's going to be a little bit easy. That's just going to be e to the x. And then, oh my goodness, what's going on? 1 over square root of 1 minus x squared. Now, this is mainly a question of being able to recognize something. Indeed, you might recall that the derivative of arc sine is exactly this expression. In other words, 1 over the square root of 1 minus x squared is exactly the derivative of arc sine. And therefore, the antiderivative of this thing is just going to be arc sine as well. So this is e to the x plus arc sine of x. And then finally, for the general antiderivative, I'm going to come along and add in that plus c that we have not yet determined. So now comes time to determine that. All right, so let's go. I want f of 0 to be equal to the value of 2, right? That's my claim. I want this to be equal to 2. But what is f of 0? Well, e to the 0 plus arc sine also of 0 plus c. Okay, I can probably evaluate that. E to the 0 is just 1. What about arc sine of 0? Well, I know that sine of 0 is 0. So therefore, arc sine of 0 is also going to be 0. So this is going to be 1 plus 0 plus c. And so I have this 1 plus c on the right-hand side. I want it to equal to 2. So I need to have 1 plus something is 2. I need that c to be the value of 1. In other words, we're saying that the c is going to be equal to 1. And so that is the antiderivative. E to the x plus arc sine of x plus c equal to 1 will give me something that is both an antiderivative and has this property that f of 0 is equal to 2. Now, this asymmetry between derivatives and antiderivatives, where there's sort of an unspecified constant c in the antiderivative, is actually incredibly important. For example, you know that velocity is the derivative of distance. So if I told you exactly what my velocity was at every single point in time, I had this wonderful velocity function prescribed to you, you might reasonably ask, what is the distance? But to get from velocity to a distance, you have to go the other way around. You have to find an antiderivative. And so you might have this lovely distant function, but there's going to be a plus c in there. You do not know where to start. So I can't tell you how far you are away from me just by knowing what your velocity has been all along, because I also have to know where it was that you started. How far did you initially start from me in order for me to figure out how far you eventually ended up to me. So this asymmetry is going to be incredibly important in a large number of our applications.